Thanks for coming. Welcome to the class here. This class is from ECG. We are a consulting firm, technical consulting firm. Let me show you this. We've been in business since 2002 and been doing VoIP and ISP design work since then. So there's a link at the bottom of this page, ecg.co/school-of-VoIP/wireshark, where you will be able to download the files that you're going to need for this class. But first, let's talk about what you're going to learn. We're going to talk about installing Wireshark, the filtering, how to do that, what that's all about. There's a few different kinds of filters that you can use. We'll talk about that. We'll talk about the network layers and encapsulation with SIP. We're going to talk about the real-time protocol, which is used for voice and video. We're going to talk about T38 FACT and DTMF. And as we go through this, we'll be able to talk about what makes it easy to design a network or hard. And so we'll give you some tips and tricks there. Feel free to use the chat session to discuss and to sort of throw in your ideas as well. But we can also use audio. We'll have some time for that as we're going through. We'll talk about DNS and NAT and quality of service and firewall issues that we can readily identify with Wireshark. There's some things you can do with Wireshark to let you do kind of rapid statistical analysis, kind of aggregate analysis of a lot of traffic. So often we're looking for an individual packet, but sometimes we want to look at all the packets all together. And then we'll talk about designing a packet capture system for your network and how you do that. So we've got nearly 100 lab exercises that you can use. And the idea here is I'm going to give you, starting in just a minute here, I'm going to give you an activity that you can do. It'll start with a pro tip here. It'll start with downloading and getting Wireshark installed. We've got a few harder activities that you can do as well. So again, here's the URL for this class, the ecg.co/school-of-VoIP/Wireshark. So you can download the exercises there, scroll to the bottom of that info page, and download that zip file. So one question that we often come to is it legal to capture traffic? This course does not provide legal advice. So to get legal advice, see an attorney. We're not a law firm. I'm not a lawyer. So you need to hire an attorney if you have a legal question. I will say for those of you who are in the United States, that's certainly not everyone here. But in the U.S., part of the 1938 Telecom Act as amended is that it says it shall not be unlawful to intercept while engaged in any activity which is necessary incident to the rendition of his service or to the protection of the rights or property of the provider of that service. So it's using the word his there to refer to the corporation running the service provider. And so basically there's a general understanding and a specific law that troubleshooting does require capturing traffic in the United States. Now this doesn't necessarily apply to all state laws. Again, I would check with your attorney, but there's an interesting paper here I've got the link to around this issue where it's actually an attorney who writes about these things and analyzes different kind of situations related to this within the domain of packet capture and computer science. So installation and filters, finding just what you need among millions of packets. So Wireshark was begun by Gerald Combs. He started the project as Ethereal, and it went on to become the Wireshark project. This was the first open source and really successful open source project for doing this this kind of packet capture and analysis and viewing that could be extended and then improved as networks improved. And so there's a lot of tools out there. There's some really nice tools from vendors that are good for doing packet capture, but this is really the open source winner. So you go to wireshark.org, www.wireshark.org to download it, and you're going to want to download the version for your platform. If you have a Windows machine, or if you have a machine that doesn't have administrator access, you can download it and install it just for your one user. Windows users, if you're using like a remote desktop type system or you have limited access to the system, to install new applications, you may be able to use the portable version that lets you just install it and run it as an individual user. So you can drop the portable version into any directory you want and use it. And for our purposes, you don't need to be able to capture traffic off the network. So if it wants to install a special driver or set up special administrator level access, if you own your computer, feel free to do that, but you don't actually need to do that for our class today. So we're going to go through an exercise here. But first, let me demonstrate here what we're talking about. So we're going to talk about using Wireshark to make a packet capture. So I'm going to open Wireshark, so I can do it the command line way on my Mac. I can open application/application wireshark.app. That's one way to do it. And it finds the local interfaces, and it finds here that there are different interfaces that are connected to different places. So one of them, the one that's actually got some traffic, is EN0. So on EN0, you can see I'm connected to a VPN, and so I don't. You can't see inside the VPN traffic, but you can see that I am connected to a VPN concentrator at this IP address. However, if we look, we can find some TCP traffic inside of that as well. So that's a filter, TCP, and I typed it in, it became green. Now, if I put in bogus characters, TCP-H, that's actually not the name of a filter, and so it turns red. And we're going to talk about how to know what these filter expressions should be. There's a lot of them, and there's some drop-down menus you can use. But if we wanted to look and see, well, let's say I want to see if I can generate some activity by perhaps accessing a web page. The one way I can do that, I will put a web browser here. We'll go to everyone's unsecure website, and we can see here do we see any traffic as we access this web page. So if we scroll to the bottom here, we can see this traffic. And if I hit the reload button here, does anything happen? Well, it turns out, yeah, something does happen. Now, I'm also streaming video to you guys, so there's always something happening in my capture. You can see here that we have 45,000 packets, but we're only displaying 12,000 of them. It's because it's still actually filtering it to TCP. So we can unfilter it, and now it shows all of these packets. But let's say there's another type of traffic, DNS, and I want to see if I can see any DNS traffic on this network. So I can type in DNS. Now it gives me another possible option here, DNS server. And I can skip that, so I'll press enter. And we have an accurate filter, a syntactically correct filter. And we know that because we have this green bar here. But the data that we've captured, these 70,000 packets, have no unencrypted DNS traffic in them. And so we can do that here. Now, if we look here at, we'll try another one to put an ICMP and see what we see. And so we've got no ICMP, but I'll bet if we ping on our local network, that traffic is not encrypted, and so I can actually see the TCP traffic here scrolling by. So here's some activity, and I can see the data coming back. So here I sent 12 packets. I got 12 packets back. A little bit of jitter here in response from my router, but I can actually see the responses, the packets here, and I can look inside them in this list. So here's some activity, even though for those of you who are using VPN, you may want to run a test like this where you ping your local gateway, what your default router is on your network, or something else on your local network, because generally that traffic is not tunneled through the VPN. So that's the gist of the activity. The first one that I'd like you guys to do is to start up Wireshark, create this packet capture of your own network traffic, access a web page, see if you see any traffic. Use DNS as your display filter. See if you see anything, check to see if you see anything recognizable. Save the capture to a PCAP file, and then close Wireshark and open the PCAP file. Now let's show you how to do that. So here we've got this. I'm going to stop this capture, and then I'm going to save. So I go to File, Save. I'll give it a name. I'll call it Test Capture 1. Now I said I want a PCAP file, and there's a couple of different formats. Like, whoa, look at all these formats. Well, there's PCAP is the one we want from the activity, so I'll pick PCAP. PCAP is kind of an older format. It doesn't give quite as much time resolution. There's a few improvements in PCAP NG, but we'll start with just using PCAP for now. So I'll start that one, save Test Capture 1. You can see here it's got the file name, testcapture1.pcap. Now I'm going to close Wireshark entirely. And if I look here on my system, I've got the Test Capture 1. And you can see here that this guy is about 78 million bytes big. So 78 megabyte file. It only took a few seconds to create that file as you guys were watching along. Now I can open that file. There's a few ways to do it. If your Mac has the application properly installed, or your Windows machine, you can open it directly. So let me see here. I'm gonna open this directory, and I can see here. Here's my list of things in this directory. Here's test capture 1. I'll double click on that. So it is loading it. It only took it a couple of seconds, so I didn't quite show you, but we got 117,000 packets here. And let's say I want to go back and find those ICMP packets that I worked so hard to produce. I can put my ICMP in. It's going to search it, and which is what you saw it doing there for a second. And then we've got the ICMP packets here. We can see that there are 24 of them, and it took 2.7 seconds to do that search for those ICMP packets. So they're displayed by default in the order that they occur in the file. So we see that frame number 80,187 is the first one displayed, and then the next frame displayed is 80,212. So that's the really sort of top the starting point. If you can do that, then you can at least open, create, and save and open files. Now, this doesn't tell you how to actually do a packet capture in a particular scenario. If you need to get a packet capture from a phone, from a session border controller, from a firewall, from a piece of networking equipment, that's a bigger story. But this is the starting point for how you're going to do it. And once you create that packet mirroring infrastructure, then this is basically how you're going to capture the data when it gets to that point. And a lot of pieces of equipment and software, they can already send you a packet capture or a .pcap file already without having to do anything special, because they already do the monitoring for you. So being able to manipulate and manage and save the PCAP files is a valuable thing, because this is how people troubleshoot. Sometimes they have to share these PCAP files with one another. So I will give you a few minutes to go ahead and do that, to download and install Wireshark, run through this activity, bring me any questions that you've got, and then we will get back going in just a couple of minutes.
What is Wireshark? Fireless.
All right, looks like we've got some consensus here. Okay, so picking back up, let's talk about some of the pragmatic factors of using Wireshark are going to be that it's going to use a lot of memory. So I did a little graph here on one of the recent versions of Wireshark. So the horizontal axis here is the size of the file, and the vertical axis, independent axis or dependent axis, is the amount of memory that was required on that version not long ago. So you can see here, if you've got a 200 megabyte file, the Wireshark processor itself is going to use over 400 megabytes. If you got a 500 megabyte file, it's going to use something over 600, maybe around 700 megabytes of memory. And so it's good to have a lot of memory. So when you're putting in that budget and say, boss, I need a 16 gig laptop, then, well, hopefully you could just extend this graph out until you hit the 16 gig line, and you'll be ready for that conversation. But it can use a lot of space. So let's talk about some of the details of how we want to customize Wireshark to be really useful. Because out of the box, Wireshark, it shows you the packet bytes down here in hex, and I know that's useful for me almost every year. That's actually a useful feature. So I don't most of the time need to show that, because it's just not a useful thing often enough. And then I've got what's in here called the packet detail. And then I've got the packet list, and then we've got our display filter and a toolbar, and then we have this white space above the window. So all those things we can customize. The packet bytes, it's usually okay to hide that, and so let's go over here and I'll show you that. So here I've got the packet bytes. You can see here this is not super interesting data. Now if I look inside, and these are the ICMP datagrams here that we want. Those are don't have a lot of interesting data. Now in ping, of course, you could specify some data. If I had unencrypted data here in this particular capture, we could look inside that, but this is pretty rarely useful. I will say there are some times that I've seen some interesting things with SIP, where the ends of line, so you'll have a carriage return line feed. If that's not structured like I've seen a case where there was an extraneous carriage return line feed, especially in new software, if you're writing a new application, maybe a call center application or a dialer, or maybe a system that automatically accepts incoming calls, like an auto attendant type of functionality, where you're having to actually write the SIP parser, then that's where that kind of error can usually will crop up. But here we don't really need that, so I'll show you. You can go up to the view menu. It's going to look different on if you've got a Windows machine. But then there's a packet bytes option. So every platform is going to give you this packet bytes option. You can choose that, and packet bytes goes away. We don't need it. When you want it back, obviously, you've got that menu again. So one of the other things to look at is the packet detail. So packet detail shows the packet's decode, and there are disclosure widgets, which are little twisty things that can be used to get more data. So you see here these twisty disclosure widgets can be expanded to get more detail. And so this is often where you're going to want to customize things to get the type of information you need. So if we look here, I'm going to make this a little bit bigger. I've got a couple of these. So this one is open. This disclosure widget is open, and so I can see that detail about the ICMP message. But I can close it up, and I can look inside the IP section. So here, this is Internet Protocol version 4, our standard old IP protocol that's been around and in active use since the mid-'80s. And we can see it's just got a summary here, source and destination IP address in the gray line. But once you expand it, you can see all the decode of everything else in the IP header. We can see there's the version number. We've got the header length. We've got the diff server field, which is near and dear to the heart of old school telecom people, because we have to use these to configure routers and switches to prioritize traffic. So we've got the diff server field in here, and then it shows it to us in all these different fun formats, including like you can see here, the hex version. So when you see 0x, that means it's hexadecimal. So 0x00. So this was there's no value here, but this is the actual field value. But this also has a name, class selector 0, CS0, in the IETF standards for per hop treatment. And so that per hop behavior of CS0 is identified with a value of 0 in the diff server field. Now this is actually the toss byte. So there are 8 bits here. So when you see it's broken out like this, this is actually bitwise. And so if you're looking at a book and it tells what the bits are in the book, then you're going to be able to look in Wireshark and see that. So here, this is all zeros. We'll look at some other examples where it's not zero, and therefore it is infinitely more interesting. We see a total length here, which is just, again, a decode of this. We see the identification, the ID field, which is not used very consistently by a lot of pieces of equipment. We've got the IP flags, and you can, again, expand inside this to get to that IP flags field. And nevertheless, eventually we get the source and destination header, but you won't find, of course, a port number, because port numbers are not an IP concept. They actually live at the higher layer protocols such as UDP and TCP and SCTP. So we've also got the ICMP part here. So we've got the values inside ICMP. We may not be interested in that, and so this gives us a convenient way to look around. We've also got the frame number here. So this is metadata about the frame. This frame data, it's important to know, was not received by Wireshark, but it was actually stored by Wireshark. So it was captured and stored by Wireshark. So this was frame 85883. This is not a frame number that will survive in general. So this frame number is referencing this particular file. So this is the 85,883rd frame in this file, but you can edit this file and remove some frames from it, and it will no longer be frame 85883. So you got to be careful when you take a packet capture. If you go and edit and filter and then try to clean it up and say, well, I'm going to give you a tidier capture, I'm going to filter some stuff out, because you don't need to see that other things. Or maybe you have to filter it out because privacy rules. You need to protect somebody else's data, so you need to filter it down just to the minimum. Well, remember, this frame number is basically a count that Wireshark generated as it loaded that file. And if you filter out something up here, then that frame number is going to move, and it's going to go to a smaller number. So that frame number is not going to survive in general as you modify the file. So if I took this file, modified it, as we may have time to do, and then saved it again, I would have a different frame number. However, the number of bytes on the wire and would actually be the same. That some of these other details would be the same. The timestamp, the arrival time, is probably the more important value, because this will survive as you move around things in the file. This is a capture of the point in time. So my system clock is set to Eastern time. It is currently adjusted to Eastern Daylight Time, and so the time on it was 13:29:16, and then we've got actually microseconds here. They're femtoseconds maybe, 407,623, and because if it was 6 digits, we'd have microseconds. So there's a lot of these. Now, something that's a lot of you may not deal with on a regular basis is, well, what's the milliseconds part? Because there's a lot of applications where just knowing the milliseconds is enough. Well, the milliseconds are the first 3 digits after the decimal place. So 13:29:16 and 407 milliseconds would be the whole number of milliseconds. But Wireshark is capturing more information than that. Now, it's also got the epoch time, which is the number of seconds since the Unix epoch, which was January 1st, 1970 GMT. And so that's just the standard time that's used on a lot of applications and systems to record a reference point, so that you can record time as monotonically increasing. But this is actually going to be the arrival time displayed for humans to understand. So this is the frame length and the capture length. So this is basically saying that the frame length on the wire, which is the bits on the wire here, 98 bytes on the wire, this was how big was the frame as it came in on the network, or in this particular case was sent out by the operating system. And then how much of that was saved, because when you do a packet capture, you may not save the entire packet. You may tell it to limit its capture to some smaller number of bytes. So for example, if you're using the TCP dump tool, by default, on most of the older versions of TCP dump, the older compiles, by default, they would filter the capture to only the first 64 bytes, because it really wasn't interesting. If what you're trying to do is make the TCP protocol work, it wasn't interesting to see the content of the email, only to see what the first few bytes of the packet were. So 64 bytes was plenty to get the IP and TCP headers, which was what TCP dump was made for, was made to be doing troubleshooting. Now you can tell TCP dump, if you're using that tool on the command line, how much to capture. By default, Wireshark and its cousin command line utility T-Shark are going to capture the entire frame. So that's why we have the capture link to record how much of the data was actually recorded. We've got some other things in here that are metadata. It's got a coloring rule name. These are the coloring rules that tell us why it's colored pink, and we'll talk about coloring rules later, but here I'm turning them on and off. But it's giving us more data. So remember, this top information here, this is metadata. This is not actually content of the frame that came in on the wire. This was generated by Wireshark. This, however, the Ethernet 2 section actually is data that was recorded on the wire. And so we've got a destination and a source MAC address. You can see here we've got the destination here MAC address, HCE2DAF2 413C. Then we've got the source MAC address HC8590A4 6B5A. So those are, there's not much more here other than a type field to indicate how to the operating system should decode the next part, but we have talked about each of these different segments. So this is the frame detail pane of the page. So that's what all this is about. So when we talk about the frame detail, drilling down in here, this is the part we're talking about. Now we got the frame list page, part to talk about. So here we see the information about the very same frames, but it is listed here. So we've got lots of frames. So each of these rows in this table, of course, represents one frame that is either was captured or is present in the capture file. So here we have the frame number, which is the number that occurs in the file, as discussed earlier. There's some sort of timestamp, but you can see here this timestamp seems to be kind of irregular. It goes from 1 to 0 to 1 to a 0. So we'll talk about that timestamp. We've got a source and a destination. Your timestamp may look different, by the way, because if you've got a new installation or you've used it at all, then you may have changed that timestamp. We've got source and destination IP addresses on this frame, so you can see how the source here was this IP address ending in .227, and the destination was .1. And then the next packet has the source 1 and go to the destination of 227. So obviously, this 227 is talking to .1, and .1 is talking to 227, is sending messages to it. We've got a protocol, which is just a summary of the contents of this, and then there's an info that is just a decoded view of something about this frame. And normally, this is very useful information. This is a summary that's useful for identifying the traffic. As you can see here, this info, though, correlates exactly to what you're going to see if you were to drill down and look in the Internet Control Message Protocol, the ICMP section, where we see the ID value of hex 9384, and we see that identifier here of hex 9384 as well. So that's shown in there. It's also got, we see the sequence number and the time to live, the TTL value, which is the number of router hops that this frame is allowed to go through. This is how traceroute works, is by adjusting the TTL. And then there's this additional information here that says reply in 80609. So this is telling you that the reply to this ICMP echo request occurs in frame 80609. Now, since there's no other ICMP traffic going on at the same time, it's pretty easy to put that together visually, but Wireshark does this for you. So there are some things that Wireshark can do to correlate between two packets, even though they're showing up on different lines here. It's going to try to do some analysis. This actually points back to the memory issue, which is that as you're running Wireshark, if you're doing a packet capture with Wireshark, then it's actually building an internal state database, in effect, of all of the frames and the messaging and the flows that it has seen prior. Maybe not every single frame is stored in memory, of course, but the things that it can understand, such as ICMP echo request, it's going to remember those for a certain amount of time, allocating space in memory, so that when the reply comes back, it can look that up and match that so that it can display it properly. So if you're using Wireshark or T-Shark as packet capture tools, so you've got maybe a laptop and you plugged it into a piece of equipment or like an Ethernet switch, and you're capturing for a really long time. Well, by default, Wireshark is going to be building this internal state graph, it's called, object graph, to record what comes in from different places on the network, and then to be able to correlate that with data later on. So the memory utilization will really shoot up if you're using a tool like Wireshark to do that kind of analysis. So there are some things you can do to do some sort of brain dead analysis where it will just record the data instead of actually doing the analysis of it. But that's also what some of the other tools are good for. I tend to use, if I'm doing a big packet capture, I tend to use a simple tool like TCP-dump, because it's simple and small and fast. And if all I need to do is write data out to the network or write data out to disk, then it gives me plenty of capacity. Okay, so that's the different sections of the page here. Now we've also got the display filter, and we're going to talk some about that. Now the one here that it shows is capture filter D4B9 capture filter. So the files all have a 4-letter code at the beginning. So let's open that file up here. So we're going to go here for the D4B9. So I open that file up. And I joked about getting a lot of memory for Wireshark, but if you do a lot of Wireshark, you're really going to appreciate having a powerful machine. And if that means using getting a virtual desktop and logging in so that you have a powerful machine somewhere, then I think I could set you up with a company that'll do that if you can't run that yourself. But it's not us. But if you can have a very fast laptop, then that can be really beneficial as well. So because this is actually very CPU intensive. Now it's only CPU intensive for a few seconds, but sometimes a few seconds or a few minutes can be a lot of delay as you're doing one thing after another. So as you're going to go through this, you can see that even though I've got a fairly fast machine, there's going to be some periods in time where it waits, and you're going to find that you're going to see some periods in time where it waits. And so you can kind of compare what that performance is between the two. Okay, so here we've opened this file. We don't have any kind of filter on at all. So we have 568 packets in the file, and we were displaying 568 of them. And we can see the contents here. So we've got a lot of different kinds of data. Now you may have more colors, and you can turn on these coloring rules. And these coloring rules will apply a filter, a search filter, and then if a particular packet matches that, then it will apply the coloring rule. So that can be pretty nice to help break things up and help you see the difference between them here. You can also see there's a preview here of what the colors are. So if we go down to this middle part, we see a lot of green, as you can see here in this middle line here. As we scroll along, we get through to the tan part. There's a lot of ARP traffic here at the bottom. So this packet capture has a lot of different data. Some of it has been anonymized, but it is available for you to look inside of. So here we have an ARP frame. This is not actually Internet Protocol. It is used to bootstrap IP, and so it's used to discover the mapping between IP addresses and MAC addresses. In particular, it's used to find out if I have a given MAC address, if I have a given IP address as a computer, to connect to the network, to transmit to the network, and ask who has that, what is the MAC address corresponding to that particular IP address that I have. So here we have an ARP who has request to find out, well, I have this particular, I want to send a frame to 192.168.31.39, but I don't have a MAC address entry for that. And so it sends out this request to get a reply back. Okay, so let's look at frame 410. So there's a packet list. We can see, as we already discussed, it talks about, it gives us some basic information about the packet. And so it also has some resolution functionality in there. So I'll show you that, where we can sort. So if we sort by source address, this gives us effectively a way to group together traffic from different addresses. Of course, it's also sorted. So we can sort by this, and so these are no longer in order of the time the frame was delivered, but we're getting all of the frames that came from a particular source, and that can be kind of useful sometimes. It sorts by time, which in this case, we've got a lot of times that are right at 0, so we'll want to figure out why that is. And then we've got the number, which is the order that they occur in the file. So if we're going to look at frame 210, you can use there's a go to packet functionality here. So I use the Command G on my Mac, but you can go to a packet from the Go menu. So we use 410. You should be able to jump down here to a familiar SIP message. You know, this was a class for people in the voice video industry. So I need to get you a SIP message just to relieve that, break that tension, because we haven't looked at any SIP yet. So here's a SIP message to break the tension. So it's a SIP register message. You can see the first thing that screams to me is there's no authorization header. So this is clearly not quite ready for prime time. We're not ready to actually create an entry in the contact database. But we've got a SIP register message. We've got the contact header that says that this user, 201-867-5309 at twotone.net, is currently at this location, 192.168.31.14, port 53217. we're going to reach out to them over SIP over TCP. So this is the full SIP URI that we've got there. So that's what we see here. And notice how I opened it up so that I could see inside the SIP register message. Your SIP register message may look a little different though, because there's another customization you now. I have SIP as raw text, and you may only have this SIP where you have to expand and expand and expand. It's just such a drag to have to expand all these. And when you get done with it, when expanding, like, this doesn't quite look like a SIP message that I'm super familiar with. So there's all this detail inside here. And what it's doing is it's parsing the details of the SIP message. So yeah, it's got a general view of the SIP, but this line here, this VIA line, isn't even exactly letter for letter precisely the way it occurred in the SIP message. It's basically a parsed display. This can be handy because sometimes you want to know, for example, what it can understand about this contact URI. You can see it understands the parameters. One cool thing is that Wireshark will give you the names of things. It'll say this is the user part, and this phone number here's the user part. This phone number, this IP address is the host part. That's kind of nice. But this is not normally the most handy view. This is a lot simpler view. So if you're accustomed to working with SIP, and often you just want a fairly compact, simple, non-decoded view. And so we'll talk about how to set that up soon. That's one of the tuning things that we want to do for VoIP. So there are a number of items here you're going to want to do on your Wireshark installation as we're going along. One of these is going to be to modify the columns to include the really useful value. So for me, looking at the source and destination ports is often really very useful, especially when you're working with NAT, firewall environments, and session border controllers, and you're having to do some sort of NAT traversal. Now that happens a lot less if you've gone 100% TCP or TLS, but if you've gone 100% TCP or TLS, then you have some other fun to work with in your network. But here I've got the source and destination IP address, but I don't have the source port, so I can't see what the source port here is. But we can fix that. So if you go into your preferences, which on Windows is going to be under the edit menu, you can go to appearance, and so you can see your appearance is an Expando Magic menu box. You can go to the columns here, and we can add a column. So here we've got these check boxes. These correspond to the columns that are shown here at the top. And we can add one, so we'll add one. I clicked on source there, and it stuck it on the end. So I'll call this one source port. I'll add another one. We'll call it destination port, DST port. I abbreviated just because I like abbreviating, and it makes it compact in the column view. So now what we want to do is get the source port and destination port. And so what I did here is I went to the type, and I can pick, and you can see these are the things that you can readily and easily choose as a column. So I can put a 802.1q VLAN ID in here. I can put the time and date, absolute time and date. I've got some things like the Cisco vSAN identifier. So this is kind of a clue that people can add in new decoders, dissectors as they need. They're called dissectors in the source code. You can put in things like the delta time displayed. So what's the gap between this and the previous frame, or the previous frame that was displayed? So all those things in here. And really what I want is the source port. So that one's one of the options here. So that's that. And then I want the destination port. And here I really want the destination port unresolved. So there's a couple of different options here. We'll pick destination port just like that. So I've got these, but they showed up over here, so I can drag them to the place that I want them. So I'll put source port there. And then I'll move destination port right after the destination IP address box. So now I actually have my port numbers on there. So that's often really useful. And if we were to scroll down so that we could see frame 401, which is where some SIP is. Actually, for 410, we can see here that the source port was 53.222. The destination port was 5060, good old familiar 5060. And so we can readily see these are in here and what port numbers are used for this traffic. Now, there's a couple of other options that we want to use while we're here. and I'll show you on the slide. So we want display raw SIP. So that's that option that shows you the non-decoded view. And then we don't really need the \r/\n. And so in SIP, the end of each line, as we look at it as humans, is to have \r, which is literally speaking a carriage return. But in the C programming language and many other programming languages, this is encoded as \r. And then the new line, which is also called a line feed character. And so \r and \n are the things that would normally appear. We don't really need that in the raw text, raw SIP display. And so those checkboxes, we want to turn that one on, and we don't want the raw SIP to show the \r \n. So we'll switch over there. We'll make that so. And preferences. Now for this one, you're going to be actually drilling into the protocol details. So we're going to have to scroll down through this long list of protocol dissectors. And here, these are the boxes you want. You want display raw text for SIP messages, and you want don't show \r \n to be checked. We see another note, someone who said, been using the custom column for SIP.csec, the command sequence, which greatly helps in matching, identifying SIP transactions as well. So we'll get time. We should get time to be able to show you how to add a custom field. That's a cool idea to use that for correlation in the command sequence. All right, so Wireshark does some decent guessing about RTP, but you can tell it to try a little harder. So by default, it doesn't try very hard to dissect the VoIP medium. By try very hard, it doesn't inspect every single UDP frame to try to determine if it looks like an RTP packet. So Michael pointed out to us that you can ask it to try harder and decode all UDP, attempt to analyze all UDP to see if it appears to match the pattern for an RTP frame. And this can help in a lot of cases where you've got a mixture of voice signaling and voice media or video media, and you need to be able to see the RTP even if you don't have the call setup information. So you don't have the SIP invite that created the call, but you want to be able to identify that the media is media and not just a random UDP frame. So this is something we can do in the analyze. We can go to enabled protocols, and then as you see here, we've got RTP UDP. So I'll show you that. So analyze, enable protocols. We've got a different kind of menu here. And then if we scroll down, these are all the types of protocols that it's doing analysis for. By default, most of these are turned on. And then here in the RTP section, I've got RTP UDP checked. And so that's what we want, to have it actually check to see if the frames match RTP over UDP. So that's a nice option, and will make Wireshark substantially more friendly for analyzing packets that have that characteristic where the call was set up at a time before the packet capture, or the call setup information is not included in the packet capture. And often that'll happen if you just start doing a random packet capture on a network. You're going to pick up some media streams. The media may or may not be important to you, but having that RTP UDP option checked will help Wireshark to decode it properly. Okay, so your project is to open the multi-protocol file, the D4B9 file, hide the packet bytes, enable raw SIP, and disable \r \n. Add the source and destination port numbers to the columns. And then I want you to open another file, the one that starts with AN0103D9, and look and find out if packets 1, 2, and 3 are decoded as RTP. Be sure that you enable the RTP UDP decoding after that, and then determine the codec type used in that call. So you can look inside that and figure out what the codec type is if you've got the time to do so. So I'll play some peppy music for the youngsters, and then we'll be back and give you a few minutes to do this. Just drop me a note in the chat window when you feel like you've got this one all taken care of. Welcome back, and thanks for working on this one. Hopefully you were able to go through this. Let's do this one together, the AN0103D9. So if you're not quite done yet, follow along with me here. So we're going to open that file and do that one together so I can show you what it should look like. So we're in the AN0103D9. So this one, this guy here. So we've got this open, and this starts off with a lot of RTP in my view, but it might not look like that for you. So the question is, are packets 1, 2, and 3 decoded as RTP? And the answer is yes. The protocol column shows that. Now, what you may have had was, could have been different. So if your RTP did not have this checked, it might have looked different. So if we do that, reload it, then you might have seen something that looks like this. This is what the packet would look like. These packets would look like if they were not actually decoded as RTP. If we had not asked Wireshark to try to decode every frame, every UDP frame as RTP. So I'll turn that back on under Analyze Enabled Protocols. Scroll back down to RTP. And get there now. I could have used search as well to do that a little quicker. Okay, so we want to know the payload type, the codec type used for that call. The codec type is the same as the payload type, so we're not going to get to cover everything about VoIP. We've got other classes where we cover a lot of things like how protocols, codecs are negotiated, and some other fun things like that, how SIP calls are put on hold and taken off hold, what the structure and the content of the SIP headers are. We've got material that covers that. We'll be glad to have you in those classes. For this one, though, we're just going to look real briefly at what the payload type is, the codec type, and it is G711 MULAW. So this is the digital audio from the 1960s, and we've got that still in widespread use. This is MULAW, which means it's in North America or Japan. If it was G711A law, we'd see that in Europe and then European colonies, including parts of the Caribbean. So we can see here that this is G711 MULAW. That's the codec type that's in use. And one of the cool things about G711 MULAW is there are some things you can look at in the actual payload. So it's giving us the first few bytes of the payload here in hex. It's giving us the first few bytes, and we can see that this is not silence, because silence would have all of the same, exactly the same letter if it was technically all silence. But if you tend to see numbers that are very high, so these are F0, F1, F2, 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 F4, F5, there's not a lot of variation in that. That may be a clue that it's pretty quiet. It's just staticky. Nevertheless, that can just be a quick and dirty way to assess whether you're getting silence. If you're getting all F, so if every letter here is an F, that means it's perfect silence, which means it's effectively machine generated. There's no microphone involved. It's just been generated automatically. And so you might get that connected to an auto attendant or a ringback generator, music on hold, or something like that. But if there's any kind of imperfection in the audio, then you would see some number other than all Fs. And of course, there is a certain amount of ability to decode and listen to audio. That's also possible on some platforms. That's not really a major part of this class. Okay, so moving right along, we're going to talk about some of the filters that we can use here. This is the display filter line. So just to get started, if we wanted to only limit our search to SIP, we could just put in the word SIP here, and it would highlight all of the SIP traffic. It would filter it down to the SIP traffic. So the first SIP frame in this file, if we sort by frame number, is frame number 1542. And we can see here that that is the SIP invite, and then there's a 100 trying and 183 session progress. There's a prac, etc. It looks like that call might actually get connected here. Here we see a 200 OK, and then you look at the command sequence and you can see that it's an invite. So that tells us that that invite was successfully completed, and we can get some clue here that this call might have gone through. Now we can You can also look at other things, like we could put the call ID in here and start looking at those. Those are some other things we'll dig into a little later. But that's the big idea. So we can do a filter, and then we can see what's happening packet by packet. It's going to throw the others away and not display them. Now, you notice there's 14,000 frames in this file, but only 18 of them are SIP messages. So if we scroll down, there are only 18 of these that are SIP. And you get a lot of frames from VoIP, because with VoIP, with media, with audio, you usually get 100 frames per second for a two-way phone call. So 50 frames per second in each direction is normal for that. So I'll show you some of the other common filters here. So we talked about SIP, but you can also do SIP contains. And so we could look for SIP contains and then a string and double quotes. And that's a way of searching. It does a full text search inside the SIP for some text. This is kind of a common, cheap and dirty way to do some searching. So for example, here we could do SIP contains 995.316. Doesn't have to be a whole phone number. But it's going to search inside that SIP, and it's going to find that only some of those SIP messages actually contain the string 995.316. So here we see 995.316 appears in this SIP message here. So that SIP contains is pretty handy. It's not very fast. So if you've got an enormous file, and then you might find that it takes a fairly long time, many seconds, to be able to search through it, maybe even minutes. You could do a filter on SIP with these parameters inside the SIP message. So the SIP header, like the command sequence header, csec. So sip.csec.method equals double quote invite double quote, and that will search for any SIP message where the command sequence is. It's actually got a typo here. This is actually invite. So the idea is that when you send a SIP request, then that's going to have a command sequence method in it of invite. And then any responses to that are also going to have the command sequence of invite, any formal responses. So looking here, we could do that one, and we'll say SIP dot. So put that in, and until I put that last double quote, it was not a valid expression. So I hit an enter there to apply, and it applied these. You can see here that this command sequence has invite in it, and this one has invite. All these, of course, are going to have invite. So these are all SIP messages where they're part of an invite transaction. And that's what that's telling you. Now, if you don't memorize these things, like sip.csec.method with all the proper capitalization, there are some ways to actually go back and look at them. For example, this is going to show you previously used filters here. So here I've got the two that I just typed in and showed you, and you can get those from a drop-down list. You can also build an expression, this expression builder, and this expression builder gives you the list of available protocols. And so we can scroll down here to SIP. Expando magic it. You can see things in here. And so you see all the possible options that you can search for. So here's our sip.csec.method as we had before. You could say sip.csec.method is present. So we just want to know if there is one of these, then that's our expression right there, and we can hit OK. And it will actually put that in there for us. Now, it makes it CRUD until I take out that other data. But here I've got a legitimate expression of, now it's showing what it used to be. But this is the actual one it applied, sip.csec.method. So this is going to match on every SIP message, because every legal SIP message has a command sequence and a method in that command sequence. But let's say we'll delete that one out. We'll go back into this, and we'll jump down to SIP again. And I could do this, I could reproduce what I showed you just a second ago, sip.csec.method equals, and then I'll put invite. And so it generates that expression that I manually typed a second ago. So basically, this is how you use the expression builder. You pick your field, you pick your relation, and then you pick your value that you want to match on. You can also look at a particular byte range and do something similar. So here I've done that. Now it hasn't applied it yet. You can see I still have RTP So you have to apply these display filters before they take effect. So you can press enter to do that. You can also press that arrow there to apply. So here I've got these 8 messages that actually have sip.csec.method equals invite showing for me here. So that's the simple way to build them and to not have to memorize them all. And that sort of begs the question, well, what else is here? Doesn't actually beg the question, it suggests the question. So the other things that you can do are you can look, for example, at all the standard headers, all the standard SIP headers that are here. We've also got a lot of the privacy related headers that are in here. All the things, this is P-assorted identity and the insider jargon format PAI. There's other here, P preferred identity shows as PPI. So somebody, when they were writing the code in Wireshark, they called it PPI just to make it more convenient for themselves. But someday I might get around to submitting a patch just to sort of spell these out once that becomes the most important thing to do that day. There's other things that you can do. So it'll have some others in here. So something like sip.resend. In certain cases, Wireshark can detect that this is a retransmitted packet, but not in every case. And so it does some analysis and it can help you on some of those things. So there's some other features here. And this list gets better all the time because people will go in and improve the SIP dissector to make it possible to do a little bit more with it. So enough on that. That's how you can look up and build those things. Let's talk about some other things here. So we've got RTP, so we can match RTP audio or video, of course. And so it will only show the frames that match that. You can look for a status code. So I want any SIP status code less than or equal to 400. So I want, in this case, it's any one that includes 400. So if we want to, we can do that one. So SIP dot. I'm going to actually do it as less than 400 here, and that's going to give me everyone that's less than. I doubt I have a 400 code in here, but if you actually had a 400 code in here, then of course less than or equal to would include it as well. So that's one to watch out for. So this would show me anything that's a SIP response code that is not in the error range. Now, remember, there are some SIP errors that are perfectly reasonable responses. So, for example, 401 unauthorized is mostly used as a trigger for authentication. It doesn't mean that an error has occurred. One of my favorite stories is the Network Operations Center, where the chief nerd in charge required that they have an audible bell every time there was a SIP error response code at all. And let's just say they went out of business. We've got also the ability to combine expressions. So for example, SIP and IP.ADDR equals 10.5.1.2. So this shows SIP messages that are going to and from the 10.5.1.2 IP address. So either from it or to it. So ADDR, IP.ADDR will match if that frame is either has it in the that IP address in the source IP address field or the destination IP address field, either one. And this idea that each of these filters is matching an individual frame, it's applied on a frame-by-frame basis, is important here. The and you got to think of it as restricting it, so it has to both match SIP and it has to match that IP address range. So sometimes it feels a little inverted from the way you might normally do it, but if you think of it as each time you add an and, then you're narrowing the field, and each time you add an or, which is the bars or just the word or, 2 vertical bars or as I'll show you, then you're widening at your, it's conjunction and disjunction. So conjunctions tend to limit and add additional requirements. RTP event is one that shows RFC 2833 or RFC 4733 DTMF. So we'll get into that in some more detail. So the display filters that we've got here, we've got several, including we can use English or C-like, so equals, not equal to, and some items like that. So you can use, for example, IP.src not equals 10.0.1.0.5. So if if the source address is not equal to 10.0.0.5, then show that packet. You can use logical operators like and or. Now you can actually use the word and you can use the word or. So this one's got and or, and you can use either one. They're identical here. You can use, there's some logical exclusive ors that you can use. This is an example of looking inside a frame at a certain byte range and then comparing that to this. And I've found a few uses for that are fun. So you can also do nesting and grouping with parentheses. So for example, we could say sib.cseg.method equals invite, and the SIP RURI, which is the request URI, contains 244.2099, or the IP address is 10.2.3.4. So if the packet is going to or from this IP address, then we're going to show it. But also, if the packet is matches this full expression of the sip.cseg.method equals invite, and the request URI contains this phone number. So if either of those is true, then display the packet. Some other examples of handy filters you can use to save the day. You can we talked about SIP contains. We talked about the SIP method. So you can look for the SIP method is invite, but notice this was only going to refine requests because only requests in SIP actually have methods. So we can look only for methods. We can look for invite or ACK, and the reason we put these together is because the invite and the ACK transactions are really closely connected. Each time you have an invite, then you're going to complete that with an ACK, because this was the SIP developer's way of having a three-way handshake. I promise I'm going to be available to send audio to me, you're going to be available to send audio to you, and I need to know when you're ready to send it to send audio to you. And so we need a three-way handshake. It's generally a design pattern of protocols where there's going to be two-directional communication. So we need that they use invite and ACK. Some of the SIP developers have said to me personally that they think that this would be something they wouldn't do again if they were going to bother to make a SIP version 3. They wouldn't bother to do it in this particular way. But in order to do that, it would not be backwards compatible. Here we can look at the RTP, and we can look at the payload type of 0. So show only RTP that has a payload type of 0, the G711 MULOG. Here we can have the call ID, so we can search for a call ID. So if the call ID is exactly this value, then we can match for it. And so this is obviously a long expression. You wouldn't want to have to type that on a very regular basis, but I'll show you some shortcuts for getting there. And so that's kind of nice, because this will show you everything involving a call ID, whether it's an invite or a refer, a register, a buy, or cancel, any SIP message that's got that call ID. And so that can be useful for looking at the lifespan, the life cycle of a call. We can look for RTP, but only RTP if one of the UDP port numbers is either sender or receiver is port 8000. So that can be pretty handy. And then we can look for inside the SIP. So we can look to see if the SIP contains M equals image, which would be a SIP with an offer, an SDP offer of T38 faxing. So you're going to have an M equals image line, and we'll show you some more examples of that pretty soon. I had a question that came in. When you say people, do you mean everyone? As in, this is open source? Yes, Wireshark is open source, and so you can get the code. It's written in C. Okay, so some examples of these we can do for here. We could say SIP dot call ID contains, and I can put in one. I'll put in BW here, and we've got all these. Now if we say SIP contains 10, then it doesn't parse, and so that failed because I don't have the matching quotes. Here's all the SIP call IDs that contain a certain substring. Now, this is where the decoded SIP can be pretty handy, because I can go down in here, I can go to the call ID and either right-click or control-click here, and then I can apply as a filter selected. So what it will do is it will create a filter here based on what I was just clicking on. So I was clicking on this call ID, and it applied that as a filter. So that's really handy, because I can see both the invite, I can see the PRAC, which is not part of the invite transaction. I can see where the call was answered, and then I can see the buy at the end. So that's pretty cool stuff to be able to put all of that together with one search here. But generally speaking, we can look for that. So let's say I want to look for the server header. I can apply it as filter selected, and it will search for the SIP server equals such and such. Maybe I just want to say, well, I may be in the server header, or I may be in the user agent header. Maybe I just want to do SIP contains. Then obviously you can edit that text and then apply it, and we actually get the same results here. So the SIP contains this particular audio code's product identifier and software version number. So when you're doing negation, you got to watch out for a common mistake, which is like it shows in the top example here, SIP and IP address not equal 10.1.2.3. That literally means match any IP packet that is SIP and has an IP address that is not 10.1.2.3. So if either of the two IP addresses in that SIP message are not 10.1.2.3, then match that packet. That's probably not what you meant, because normally you're going to be interested in excluding traffic. You might commonly be interested in excluding traffic that's either going to or from a certain source. So maybe you have a very busy server and you want to see all the SIP messaging that is not going to that one server or to that one IP address. Well, that's what you would do instead with this bottom one here. We would say SIP and then we would negate the grouped expression IP.addr equals 10.1.2.3. And so by negating that, we're saying match any packet that is SIP and no IP addresses 10.1.2.3. So not the IP, the source and not the destination. Both of them have to not be 10.1.2.3. And that's more commonly what you're going to want in many cases. Now, this is legal. You could use this for some use cases, but this is the one where you're probably going to be using it more regularly. So watch that. It will even put this one in yellow for you. I'll show you that. Just to warn you, because this is such a common thing. So IP equals 10.1.2.3. Of course, that one's fine. If you say not, then it says, as we can show here at the bottom, it may have unexpected results. See the user's guide. So that's what that's what it's warning you about here. Okay, so display filters, I'll give you a few minutes to practice with that. So you've got a couple of files to open up. One is PUBLD2D93. And you can build display filters for use display filter SIP, count up how many frames, SIP frames you see, and by count up, I mean look in the right place. Use the display filter RTP, practice that. And if you've got time, which we may not today, you can look at frame 543. And then I want you to take these challenges to do these, build display filters that show these different things here. And then in a different file, if you've got time, look in and see whether we've got the, how many IP HTTP frames don't involve a particular IP address. So we will give you a few minutes to work through that. Okay, so welcome back. We are going to continue here. We're going to look at some of these projects. So in the PUBL2D93 file, we wanted to look at SIP and find out how many SIP frames there are in the capture, and then RTP as well. So we'll do that over here. We're going to open the PUBL2D93 file. And we're going to remove our filter. There's 4,269 frames in this file. We'll have the SIP filter. We see now there's 14 frames in the file. If we look at RTP, we can filter that way with the RTP filter. So that's how you would filter down and look at the individual traffic for something. You notice here we've got good old European PCM ALAW companion there for that the codec type. So we also wanted to see what is wrong. What's the fun with frame 543? So if we jump down to 543, Command G. Here. We might not be able to go there if you try that if it doesn't match your current filter expression. So in this case, it says Ethernet frame check. So here, let's expand this. It's red. Frame check sequence incorrect. And so what it did was it computed that there's actually an error in this. So it actually computed the frame check sequence, which is in Ethernet a type of checksum to check the whether the frame has been sent with integrity, whether it's been corrupted. And so if you actually had something like literally cosmic rays that were modifying the contents of memory, or you had a bad fluorescent light or something like that in your building location, then that sort of thing would actually create the scenario that is shown here, where you have the frame check sequence is set to it appears as the wrong value on the in the frame. So we can infer from this that there may be something wrong with the cable of the infrastructure, especially if you were to do a packet capture and see this a few times. Now we've got some display filter expression. So this one, we want to display all the SIP invite requests. And so we could see the the SIP invite requests. There's a lot of ways to do that, but the one I showed you already was SIP.method equals invite. So all those invite requests, all two of them are shown here. Next project was add a display filter that matches all the SIP invite requests and the responses. And so we can do that with SIP.command sequence.method. So based on our knowledge of SIP, we know that the command sequence is going to be include the method of invite in both the request and the responses. And again, I'm not able to go into a ton of detail here, but we've got another class where we can talk about that if you'd like to see that. So the next one we've got here on our list of projects is to include all SIP request responses, cancel, and ACK messages. So invite, request responses, cancels, and ACKs. So we also want to see those. And so formally, the way it's written, I would only want to see SIP.csec, sorry. So this will show me the cancels and the ACKs. And what's interesting here is that, of course, we add an ACK message. I'm going to tidy this up a bit. We see an ACK message, and the ACK message has a command sequence of including ACK, not invite, even though ACK is really part of the invite process. And so that can be kind of important to see that that's happening. If you don't have the ACK, then what you're going to have is the final response is going to be retransmitted a number of times. And if the ACK never comes through, then the answering device, the call-led device, the UAS, will actually terminate the transaction. So it might kill the call. It might terminate your dialogue. Okay, and then we want to look at D4B9 and see how many HTTP frames don't involve this particular server IP address here. So in the D4B9 file, we'll open that one up. Clear my filter. How many HTTP frames don't involve that particular server IP address? So if we just want to look for HTTP frames, we can put in HTTP without trying very hard. We've got that. Now we do see that this IP address is in here. So let's do some quick stuff here. We can type this in. So I'm going to go in here, and we've got the source. I'm going to apply as filter selected. So I've got IP.source. Nice thing here is that gives me the IP address. Now I can go back and edit this. So I can put IP.addr. So that will show me all of the frames that do involve that. But really, I want all the frames that kind of don't involve that to be considered. So let's exclude that. So this is all the frames that don't include either traffic to or from 69.174.114.239. But I really, at this point, I want to limit this down now to HTTP. So I do a limit with the AND. So it has to both be this, match the one on the left here, which is this not IP address ADDR equals 69.174.114.239. And I need to match for each frame the part on the right, which is HTTP. And so these are the only 4 frames that are left. And if I had a long list and I needed to count this up, remember you can go to the bottom here and see displayed. Okay, so I think maybe I saw that one of our participants had a question. Included the plus question. I see what Val's saying there. So good work there. Thanks, guys. So we will move from here. So filtering for basic SIP, we can use the SIP to view the SIP messages, and we can see a little bit of a summary portion, but you can also do some cool stuff by applying a header as a filter. Like I showed you with the call ID, we can apply as filter. And so we'll probably have to jump past this one a little bit, and I'll just show you kind of what this looks like. But in this file, we're going to go to frame 5, and then from here, we're going to locate its call ID and apply that call ID. And then we're going to identify the UDP port number defined for RTP media in the SDP section of the SIP invite. So that'll be a little SIP analysis project, and then modify the filter to show both SIP messages along with RTP for this call. And so let's start here. We'll go to that file, the ECG LDC2E file. Clear my filter. And here I'm going to go to, I'm going to locate the invite in frame 5. Now I've got the call ID here. I can't do a filter. If I apply a filter here, it will let you do, then it's going to match it based on the exact way that is spelled. Officially, the call ID can be represented even as long as it has the correct call ID in the middle. The spelling of the letters call-ID don't have to be capitalized the same. And also, you don't have to have a space or exactly one space. You can have multiple spaces. And then you can also have a different amount of white space at the end. So this is kind of a fragile way of doing it. So I'm going to guide you away from that. We're going to take that one off. And I'm going to point you to going in here to the decoded version and applying it here, because this is the version, as you can see here at the bottom, here, call ID header sip.call ID. It's actually been parsed. And so the Wireshark has done some more analysis on it. And this is going to work in some scenarios. It's going to be more reliable. It's going to work in some scenarios where the call ID string is not going to work. So that's why I'm pointing you in this direction. If you were writing software, you would only want to do it this particular way. And if you're doing it for yourself, then for troubleshooting, sometimes you're going to go down a blind hole because it'll be confusing. Like, why isn't it showing all that SIP? So here's how to do it reliably. So we've got our call ID in here. Now we've applied that, and we've only got the traffic related to this call ID. Now, the other part of this project is I want to go find the RTP for this and filter for that as well. So show me the RTP as well. So I've got the SIP, but I also want the RTP. I want to get both together in the same packet capture, in the same view. So what I can do is I can look at this SIP and see what the port number is. So here I've got port number 16414. That's in the M equals audio part. If there was a fax in here, a different M equals line, or if there was an M equals video, then there would be more of these to do, but there's only one. So really, I'm going to add in here an expression that says I want to see the RTP going either to or from port 16414. So I've added or UDP.port equals 16414. And I can apply, and now I've got both the SIP traffic and the UDP RTP traffic together. Down here at the bottom, we're going to see where the call is actually disconnected here at the end. Now, again, there are some things from your SIP knowledge that you'd want to think about if you're doing this kind of troubleshooting. For example, what if the RTP is renegotiated to another port number later? Well, you may need to chase that around. You may have to get all of the port numbers throughout the entire duration of the call. What if the call is transferred? So it starts with one call ID and then at the end it has a different call ID. You're going to have to chase down those refer messages as well. So there's a lot of fun things that you might need to do to track that down. But in a simple call, if the sky is sunny outside and it's a simple call that you're looking at and you need to sort of pull this out, then this will get a basic call for you, because we're getting both the media going in each direction, both from 16414, but also going to 16414, like in this case. Okay, so time display format. This whole time I've been showing you these packets with this crazy timestamp. The timestamp was useless. Well, time display format is a really powerful tool that you can use. So there's a lot of different times you can use. For example, you can have just the whole date and time of day. You can have the some others that are useful, a second since the beginning of capture, so that just counts up. You can also just specify how much detail you want. I suppose for the next level down from microseconds is really nanoseconds in this display. And so here I'm going to go to view time display format. I'll put it in that format so you can see that this packet capture was taken in 2011. And this is a convenient time of day format for the file. So now if I sort by that, then I'm legitimately putting them in the right order. But there's another really common time display format, which is a couple more of them. Second since the beginning of capture. So that's pretty handy. So that means that the capture started at time 0 and then everything went up from there. And so I can see here how this is proceeding. So 18 seconds after the beginning of the capture, we have the end of the call. But then there's one more that's, but wait, there's more. We have the second since previous displayed packet is also very useful, because this gives you some sense for the timing of things. So for example, the time between the sending the invite and the response, the 100 trying response, was 0.086 seconds later, which is, if you remember the milliseconds tip I gave you before, you look at these first 3 digits after the decimal place, it's 86 milliseconds. Now, I don't know about you, but 86 milliseconds makes me kind of itch, because that's actually a fairly high number. And then we have a 401 unauthorized that comes back from that. Then that is 11 milliseconds after the 100 trying there. And then we get the ACK, and there's a short gap between that. And so you notice that this is 5 milliseconds, whereas this response time was actually, almost 100 milliseconds after the original invite. So there's a long delay between the invite and getting the response back. But then when we send the ACK, which was from 192.168.1.105, it was very fast. So the delay on the packet capture between when the packet was sent, or when the response was received, and when the next packet was sent, very, very small. So we're looking at 5 milliseconds here. This is a clue, but not certain, that we are actually looking at a packet capture that was created close to 192.168.1.105, because the delay is very short there. And so often if you have a very big difference, like orders of magnitude like this, we have 5 milliseconds versus 10 or 90 milliseconds difference between the two, then that gives us a clue that one of these is close to us and the other one is not. This actually becomes this major issue in packet captures, because you sometimes need to know where on the network the capture was taken. For example, let's say we've got a phone that's plugged into an Ethernet switch, and then in that Ethernet switch, there's a port mirror down to your laptop. Of course, you have to have a mouse. And then that connects across to a router and then across the big I internet, and then it goes to your VoIP service provider. Well, if we're doing the packet capture here, then the delay between that phone and your packet capture is going to be very short, of course. And the delay from the laptop to the voice network is actually going to be fairly long. And so we're potentially we could have a relatively a big difference between our local capture and our remote capture. Okay, so we're going to finish it here. I'm going to put these exercises up, and we will. I'll leave it with you here, and just feel free to sign off after you get a chance to finish these up, and then we will pick back up. Again, I apologize for the delay in the Zoom waiting room there. Cost us a few of our minutes this morning as we were getting started. So take a look at these, see if you can finish these up. Feel free to drop any questions in the chat window here, and otherwise I will see you on Thursday. Actually, folks, I'm going to say mea culpa. The schedule, this class was set up to go till for another 24 minutes, so we'll take advantage of that time. So feel free to finish these up, and then we will continue. Okay, so we're going to take a look at this activity here, where we see the different um, methods of determining the SIP involvement with the call. So we use the word involved. So we want to only get the traffic that matches this particular phone number. So I use SIP invite or SIP contains to do that, and it sees the register. It also sees the invite. And so we've got a we want to apply the filter that only shows SIP only for that one call. So we're given a hint here. There's only one call. So here's that call. So I will do the filter here. I'm going to look at the call ID. Use that method again. Apply that call ID. Okay, so if there is a call, determine how long the telephone call was. It looks like there was a call because we've got an invite. We've got a 200 OK for that invite. It looks like there was a call, and we want to know how long that call was. And so we're going to view, I'm going to use the time display format to do that. So here we see this is when the call was connected at the 200 OK, and then this is when it was disconnected. So it's the time between 9:47:26 and 9:47:34. That's the time. So those 8 odd seconds is actually just 7.9 seconds or so there is actually the amount of time. If it may be a little easier for doing the subtraction to put that into seconds as the beginning of capture. And here we've got 94.7 minus 86.8. And so that will tell us the duration of the call by the definition I'm using there of duration. We could say, well, the call might have begun here at time 85. When did the person dial the call? And there are international standards bodies that have actually written documentation on what that time duration should mean. All right, so determine who hung up the call. Was it the calling party or the call-led party? So just going based on IP address here, which doesn't always work, the calling party appears to be coming from .230. The call-led party appears to be .190. And so the question is, well, where did the buy come from? It came from .190, who represents the call-led party. So without trying very hard, since these are two different IP addresses, we could say, well, it was the call-led device that actually generated the buy, that transmitted the buy. Now, this isn't always a definite answer on who caused the call to hang up. It could be that this guy, the caller, said, I hate you and I never want to speak to you again. And so the call-led party hung up based on that trigger. So there could be some sort of motivation that a particular party might have to disconnect the call. A more serious example is on a fax machine, where one fax machine will actually tell the other fax machine, we're done here, and then the receiving fax machine actually disconnects the call. And so you actually can have cases where, due to the communication protocol, whether it's human level or 1970s faxing level, where there's some way that you can actually signal to the other guy to tell them to do something, and they do it, and therefore you see the buy come back from them. You can also see cases where nobody intentionally hung up the call, but you've got, for example, a bad FXS port. So you've got an analog connection, and the analog connection is flimsy, and so it gets disconnected, and that triggers the sensor to detect that they're now disconnected, so it's going to hang up the call. So it could be that neither party intentionally hung up the call, but that one of the devices detected a fault, and therefore it hung up the call due to that. So there's a lot of reasons that you'll see a buy message that are not the same as an intentional and clean hanging up of the call. Okay, so call-led party disconnected the call. So there is a full display filter reference here at the Wireshark documentations. You can go to the SIP webpage, and it will have a full description of all of these in here. So you don't have to only look inside Wireshark to see what they are, but it's basically the same as what you're going to see in your Wireshark help there for filters. So we've got other filter projects here we can do here with this particular project. One of them is to build a filter showing only SIP with authorization using MD5. We'll do that one together. So I'm going to open the AN0905. I believe, oh, here one got skipped accidentally. There's no need to memorize all these Wireshark terms as I've shown you. You can go in here and find them in the builder reference. So this is one SIP.auth.algorithm. So SIP.auth.algorithm equals MD5. And so that's the one we want. So filter SIP to only use the MD5 algorithm for authentication. So this is the slide you wanted to see so that you could go down here and find SIP.auth.algorithm in order to do this activity on the next page. So build a filter to use to show only SIP with authorization using the MD5 algorithm. And so for this, we can jump over here. And in this one, we want to use the AN010905 file. And here, we were told we want to build a filter. So I'm going to use the filter expression builder here. I use SIP. We use SIP. And we want to only use a particular authentication protocol. It's actually the auth algorithm is really the one we want. Equals MD5. I'll apply that. And here we've got all of those SIP messages that match that. So one of the other things we want to do here is build a filter that shows the syslog messages, and another one where we should limit it so that the level is not 5. So in this file, we have some syslog messages. So you can try just by typing syslog, and sure enough, that turns out to be one. So we've got a lot of SIP messages in here. This was actually an audio codes gateway. You can set up logging, so audio codes will send the logs via syslog to a particular IP address. So here we have logging set up, so sending these message logs to via syslog. You can see here that we've got a level here. Normal but significant condition is 5, and so our syslog level is 5. So let's filter on that. And now we want to show syslog messages where the level is not 5. So apply as filter not selected. And so it does the negation for you here. So I can see every syslog message that is not 5, but this isn't quite right, because what I've done is I'm seeing the a lot of stuff that's not syslog at all. So this is a case where I actually do want to use syslog.level not equals 5. It's because there's only one level parameter in the syslog field, in the syslog protocol. So there's only one place. So it's not like you could either have 5 and something else. You can only have 5 here. So in this case, is a warning condition. And so it actually gives us these are 2 SIP messages that have a warning level of 4. Finally, we want to build a filter matching all SIP registration 200 OK messages for registrations lasting more than 30 seconds. Okay, so here we've got SIP, and we want to look for the SIP 200 OK messages for SIP registrations, and we want to look for a particular duration of the SIP registration. So let's find out what that looks like, what those are going to look like here. So first, let's go back over here. Let's start with some SIP. We'll look for SIP here. Do we see any register messages? So we can see here, yes, here's one. Here's a SIP register message for a 200 OK. And the registration is going to last more than 30 seconds because the expires field has expires equals 60. And so what we really want to do is find other SIP 200 OK messages that are set up like this one. So we want to find who was allowed to register for more than 30 seconds. I'm going to do that by, first we're going to have to build this up. And so we're going to say, well, I definitely want it to be a register method. So I'm going to apply this as filter. So sip.csec.method. So I've got it narrowed down to register related traffic. Now I also want to apply the status code of 200. So here I can apply and selected. So I've got all of these. So now I've got it automatically built by doing the and selected. I've got SIP csec method equals register and SIP status code equals 200. And so that is looking good, but I haven't filtered these down to see what the expiration time is on any of these. And so if we look here inside, we can take advantage of the fact the contact header has been parsed. So this contact parameter expires equals 60. does add a particular field here. So let's see, of all these are, actually all of them have expires equals 60. So what I would have to do is, if I wanted to find these, what I've got is a bunch of SIP messages that have a contact parameter that is, all of them are for 60 in this particular case, but what you want to do is build a filter of that would handle the case where there are other values as well. And so we can look for this. Now, if we just add this one and selected, then we are going to literally match on the value expires equals 60. In a case like this isn't quite right, because we don't that would not match a case of expires equals 31, but we really do want to see that value. So let's see what we've got here if we search, if we've got a better way of doing this particular one. This one's a challenging project. So SIP expires, let's see if we can just apply SIP expires greater than 30. Now, I believe this is going to just match on the expires header, and in this case we don't actually have an expires header. So because there's no expires header, that one's not going to work. So we can look at some of the other fields we've got here. So the expires header is not quite right. We could look at the contact header, which is usually where the expiration is put in most SIP registers, and see if we've got anything there. We could look at the other fields we've got here, looking for something that will match. Well, there's one way of doing this based on the spelling of the field. So we can actually use a regular expression search and do this. And I'm going to, for the sake of time, I'm actually going to let you guys play with this one. In the SIP, we can actually match on regular expression. So we can see if we can give an idea for what that would look like. SIP contact parameter equals, we need it to be 2 digits, and we need the first digit to not be a number starting with a needs to be 2 digits. It's allowed to start with a 4. I think the challenge here is we would have longer expressions as well. So building a regular expression. So for example, we could do see if it will match on this expression. Might have to work on this one a little bit. This one's challenging because we're wanting the SIP.contact. Oh, that's not right. There we go. So this one expires equals, I'm looking for 2 digits where the first digit is a 4 through 9, second digit is 0 through 9, but that's not quite right, because if our expression time is 300 seconds, then this one won't be allowed. So we could do, we could make this a little bit more sophisticated and build something out, but I'll bet there's a more direct way of doing that. So this is an interesting challenge that that's new to the class. I don't remember right off exactly how to do it. But I think regular expressions may be a way to get there. Okay, so next we're going to talk about the layers and encapsulation here. So understanding some of the deep tools that are available. So every protocol can have another protocol inside of it. So for example, an item has a serial number, it has an intended recipient, it has a specific use. Inside the box, if you're thinking of a delivery from a mail order delivery, the box has a source address and a destination address and a bill of material. and then that box can be put inside of a truck, and that truck has its own license tag and a series of stops. So at each layer, whether it's the item or it's an item inside the box, or it's that box is inside of a truck, you have a series of encapsulation where you have one item inside of another item. And that's what we see inside protocols. For example, we have the Ethernet header, we have the IP header inside of that, and all of this would be considered the IP datagram. And then you have the TCP or UDP header, and then inside of that, you've got the particular payload. And so in this particular case, we have a snippet of an email message that's sent in as the payload inside of a TCP header, which is inside of UDP, which is inside of Ethernet. So we have the encapsulation. That's what we really see here. In Wireshark, we see that encapsulation illustrated with, we have the top layers, for example, the Ethernet layer, and then here we've got SIP and UDP inside that SIP message. That UDP is inside, sorry, the SIP is inside UDP, and the UDP is inside Internet Protocol, and the Internet Protocol is inside Ethernet. And so that's what we're seeing that Wireshark is showing to us inside there. And so we get to visualize it pretty easily by looking at the packet detail view there. That metadata, as I've already discussed, is not actually on the wire. The information about when the packet was received and how many bytes were in it is maybe inferred from what's on the wire, but it was not actually received data. So they're in VoIP call processing with Ethernet, for example, using Ethernet, we have the layers. And so we have RTP. RTP is inside TCP or UDP, generally UDP. And then we have Internet Protocol that's inside that. And then we've got Ethernet. And it goes across the Ethernet networks, goes up to IP routing, looks at those destination headers. And it's not that the TCP and UDP headers or the RTP or SIP are not present here inside the IP routing layer. It just ignores them. It just sends the traffic through. And then you've got the Ethernet traffic sent through across Ethernet to another side. So we have different domains of Ethernet, different Ethernet switches and different Ethernet point-to-point links. And that ultimately the SIP software on one side talks to the SIP software on the other side. The intermediate steps don't really care about one another. And so those are the layers that we see inside here. So if we look at this frame, then we're going to be able to see the different layers that are inside of it. So let's look together at AN0103D9. We'll open that file up. So this is the file with RFC2833 in the file name. And we want to look at frame 8560 in this one. So jump down to 8560. Okay, so here we've got, it says payload type RTP event DTMF8 end. And so what is the highest layer protocol in that frame? Well, it's basically the bottom of the list. So the bottom of the list here is RFC2833 RTP event. And so we found an RTP event for DTMF. So that's really the highest layer. What's it coming from? Well, we can look at this as coming from what appears to be an Acme Packet device. So this is an Oracle SBC, an Acme Packet SBC at that layer. But that's actually what's transmitting the frame. And so that gives us a clue. This is some of the automagical resolution of names. It's going to be based on these numbers here. And then the frame is going to be going to, in this particular case, is going to an audio codes device. Now, if you took this and you look it up, so of course I'm reading in here a lot out of these letters here. But if you took this MAC address and looked up the first 3 octets, 00908F, in the IEEE OUI database, the Organizational Unit Identifier database, you'd be able to find that this is audio codes, and you would find that Acme Packet is now owned by Oracle and some things like that. And then the question is, well, what's the payload type was our last question on this problem. So the payload type inside the real-time protocol, payload type is 101, a dynamically allocated payload type, and it's been assigned to telephone-event for this call. So those are some of the things that we can get out of this by looking at the different layers inside the RTP frame. So we also want to look at we have another project here, which is look at frame packet number 8600. So this is we're promised this is going to be a G711 MULAW packet. And so it doesn't represent a non-silent sample of audio. Like I mentioned, silence is encoded, perfect silence is encoded with all Fs, which is in binary, that would be all ones. And then we want to look at what's the duration of the sample, and remember that each byte of RTP payload is 1/8000th of a second under the normal capture time. In fact, that's intrinsic to G711 MULAW. So we can look at that in frame 8600. We'll see this, and we'll see, no, it doesn't look silent because it's not all Fs. It's not perfect Fs here. And then the other question was, what is the duration of this frame? What's the duration of audio? And so if we look at this frame here, we want to figure out what the actual size of the frame is. So we've got a little bit of information. If we jump over here to the setup frame, we won't see the actual side. The payload here we can see, but we can't see the whole thing except for Wireshark gives us a little bit of data. It says it's 160 bytes. So if each of these bytes represents 1/8000th of a second, because the clock samples every 8,000 times a second, generates 1 byte of output on the G711 DSP, then that would tell us how long this is, and this works out to 20 milliseconds. So without showing you the arithmetic there, 160 bytes times 1/8000th of a millisecond is going to be 0.02 seconds long. Okay, so we're going to pause it here and pick back up next time, this time for real. I'm sorry about the fake out. Earlier on, we're going to pick back up with the SIP messages ladder and move on from here. I'll hang out on the chat. If you've got some questions here, feel free to bring them up. Thanks very much.